Welcome to this explainer. If you're here, it means you're ready to absolutely smash past the traditional limits of computing. Today, we're setting the stage for a really structured, deep dive into the foundational concepts of parallel computing, looking specifically at the essential first steps of CUDA programming. Look, in today's landscape, which is totally driven by massive AI models, deep learning, and just enormous datasets, sequential computing simply can't keep up anymore. CUDA is the bridge that lets us actually leverage the sheer processing power of modern GPUs to handle these titanic workloads. So, we're going to break down exactly what it takes to shift your mindset from sequential programming to parallel execution, looking at the core principles that make accelerated computing possible.
Here's our quick roadmap for today. First, introduction to CUDA programming. Second, essential course prerequisites. Third, sequential versus parallel work. And finally, fourth, measuring computing performance.
All right, Section 1, Introduction to CUDA Programming.
Now, this quote from the source, "Data is nothing, structure is everything." I love this because it hooks us right into the exact mindset you need for efficient parallel programming. In traditional programming, we often obsess over the data itself, right? But in the world of CUDA, you can have all the valuable data in the world, and it literally won't matter if you can't structure its flow to thousands of processing cores at the same time. Think about it this way. If you have a massive array of numbers to process, organizing them so that thousands of memory fetches happen simultaneously rather than one by one, well, that's the difference between a program running in seconds versus hours. How you organize, align, and distribute your data across the memory hierarchy is what actually unlocks the massive speedups that GPUs offer.
Moving right along to Section 2, Essential Course Prerequisites. Before we jump into the GPU magic, take a quick second to mentally check off these 5 main prerequisites from the syllabus. You really need to make sure your foundational knowledge is ready for the leap to CUDA. You need a rock-solid grasp of standard C or C++ programming, since CUDA is an extension of those. You also need a firm understanding of fundamental algorithms, because the mathematical logic of how a problem is solved doesn't just disappear when you go parallel, it gets multiplied. Finally, you need mastery of data structures, a deep comprehension of computer organization, and practical knowledge of operating systems. If any of these pillars are shaky, the architecture of your parallel applications is inevitably going to crack under pressure.
Let's look at a little bit closer at a few of these, starting with data structures. You need to know exactly how to store, access, and modify data structures, like your arrays and standard structures, completely seamlessly. Why? Because in parallel computing, data flow is absolutely everything. A poorly structured array in standard C++ might just run a millisecond slower. No big deal, right? But in CUDA, if 10,000 threads hit that same inefficient structure all at once, that inefficiency is multiplied 10,000 times. It'll effectively grind your massive GPU to a halt. So your ability to manipulate these structures in standard C++ completely dictates your ability to scale them in CUDA. Now, let's see how this builds into computer organization. We're stepping down to the hardware level here, where understanding how a computer actually works is vital. We aren't just writing high-level software anymore, we're basically directing traffic on the silicon. You have to understand system clocks, processor frequencies, and exactly how the data and address buses shuttle information back and forth. Think of the bus like a physical highway connecting the processor to the memory. If that highway is too narrow, meaning it has low bandwidth, it honestly doesn't matter if your processor cores are the fastest on the planet. They're just going to sit there completely starved for data, waiting for the trucks to arrive. If you don't understand these physical pathways, you simply can't optimize for them. And finally, for our prerequisites, a solid grasp of operating systems is totally non-negotiable. We're looking specifically at how memory is managed, how storage is utilized, and how access paging works. Access paging is essentially how the OS continuously moves blocks of data in and out of active memory, behind the scenes. You really have to realize that transferring data between the host, which is your main CPU, and the device, your GPU, is incredibly slow compared to operations happening directly on the GPU itself. Poor memory management across that gap will just instantly destroy your performance. So, understanding how the OS pages memory is going to prevent some truly devastating bottlenecks in your future CUDA code.
Section 3, Sequential versus Parallel Work.
I absolutely love this real-world analogy from the source material. It brilliantly illustrates the severe limitations of sequential work. Imagine your task is digging a massive 20-meter hole to preserve water. Your available resources? Exactly one worker, holding one shovel, and just to make it truly painful, that shovel only has one tooth. This is sequential work in a nutshell. One instruction executed one after another by a single processing entity.
So let's do the math on this single worker scenario. With an efficiency of digging 1 meter per hour, the total time to complete the 20-meter hole is a grueling 20 hours. This is the perfect representation of a single-core CPU running sequentially at a set clock frequency, like 2 gigahertz. It really doesn't matter how fast that single worker swings that one-toothed shovel. Eventually, the sequential math just takes way too long. To solve larger, modern computational problems in a reasonable time frame, we simply can't rely on the one-worker model anymore. So what happens when we switch to a parallel model? We bring in 1,000 workers with 1,000 shovels. Suddenly, the hole is dug in minutes. But that introduces entirely new problems. If those 1,000 workers aren't organized properly, they're just going to bump into each other, hit each other with shovels, and get stuck at the edges of the hole. Which links right back to our earlier rule, right? Structure is everything.
Which brings us to Section 4, Measuring Computing Performance. The source outlines 2 main goals to achieve when you're designing parallel applications, and placing these side by side makes the distinction crystal clear. On one side, we have performance. This is the capacity to reduce the time it takes to solve a specific problem when you add more computing resources. It's entirely about saving time. On the other side, we have scalability. This is the capacity to increase or maintain performance when the complexity or the size of the actual problem increases. Basically, performance asks, can I do this faster? While scalability asks, can I handle a problem that is 10 times bigger?
But as the source astutely points out, you can't just scale infinitely. You're still going to face very realistic physical bottlenecks. Specifically, there are 4 primary architectural limitations that govern parallel design. First is latency. That's the physical delay before transfer of data even starts. Second is bandwidth, like we talked about, the maximum width of your data highway. Third is data coherency, which is a huge one. Imagine our 1,000 workers digging that hole again, but they're all looking at completely different outdated blueprints. Data coherency ensures every single core is looking at the exact same updated truth at the exact same time. And fourth, pure memory capacity. These are the strict physical laws of the silicon universe that your code has to navigate.
And that leads us to the ultimate question. The source hints at a second category of constraints, algorithmic limitations. As we continually hit the physical limits of hardware, maxing out bandwidth and minimizing latency as much as physics literally allows, will the efficiency of the algorithms we design become the true final frontier of parallel computing? I'll leave you with that provocative thought. It's a challenge that should definitely keep you eager to start writing, structuring, and testing your own CUDA code. Thanks so much for joining this explainer.